All right, so we're going to be talking about the binomial expansion theorem. Now, a lot of y'all have done this before, where you have these two numbers, you have this square, and you actually use like the box method or FOIL or what have you, and you expand this by hand, okay? And it's not too bad when it's squared. So what this says is we're going to write this twice, and we're going to FOIL this out, okay? You do the first two, you get x squared. You do the inside, which you get x dx. You do the outside, which you also get x dx. And then you do the last, which you get dx squared. And since those are the same, you can combine those and you get x squared plus 2x dx plus dx squared. Okay? And that's fast enough, but what if there was a third one? Right? What if this wasn't x squared? Or what if this was x plus dx to the third power instead? Well, then we'd have another set of parentheses over there, and then this right here, you'd have a whole bunch more lines to connect those multiplications. Well, there's actually an easier way. It's quicker, and we're fixing to go over that, right? And as this number increases, this gets harder and harder. So let's go over what we know as the theorem. So the theorem states that we have the summation of a number that starts at 0, a position that starts at 0 and goes to what we know as the exponent. We have these indexes where this is position, this is our starting exponent, and this is the subtraction of those. Where we have, that's supposed to be an I, not a J. Okay? Apparently I like writing J's instead of I's. In our case, we have our power of 2. So our n is going to end up being 2. We have our summation from j to 0 to 2, 2i j x to the I dx to the j. And we're going to actually write out what the summation is. So from our first position, it starts at 0, that's given to us, so we're going to have 2, 0. And then this number is just 2 minus 0, which gives us a 2. And then we're going to have x to the I, so that's going to be that 2 there. Dx to the j. See, I wrote j instead of the z. Yeah, and since it's a summation, we're going to put a plus sign. And we're going to do it again. But this time, we're going to increase that position by 1. And then we're going to subtract, and we're going to get 1 there. So this is going to be x to the first, dx to the first. And we do it again until we get this first number here as a 0. We're going to keep doing this. Plus 2. Next position is a 2. That's going to be a 0. So this is going to be our last term in this. This is going to be x to the 0 dx squared. All right, so now we have to know what these positions are. 2 choose 2. That's just 1. Okay? Whenever these two numbers are the same, it's just going to be 1. So this is a 1. Anything to the 0th power is going to give us a 1. So we drop down as that's going to be x squared. When we have this number is 1 less than the n, it's just going to be the n. So this is going to be a 2 x to the first, dx to the first. And then again, this is symmetrical to this one, so it's going to end up being 1 as well. And anything to the 0th power is 1. So we have dx squared. Now, for the power of 2, this is a little bit slower than using the box method or foiling it out or what have you. So why would we do this? Well, again, if we change that to a 3, which we're fixing to do, we're going to write this out, but we're going to have one more term when we write it out this way. Whenever you have to multiply that out, you have a trinomial times a binomial when you multiply that out. No one wants to do that. No one wants to do a 4th term polynomial times a binomial. No one wants to do that. And so doing it this way, it just increases. And these coefficients here, depending on the position and the row, so this number gives you the position, this number gives you the row on Pascal's triangle, you can find those numbers pretty easily if you know what Pascal's triangle is, which we've done a video on. You can go back and watch that. So, let's try this to the 3rd position, to the 3rd, okay? I'm going to start over here. First term is going to be given to you as 0. This is going to be x to the n dx to the 0, so x to the I here, and then dx to the j. This is going to be a 2. That's a 1 because 3 minus 2 is 1. I did that backwards because that's going to be 0 and then 1 because I did my positions wrong. X to the 2nd, dx to the 1st. Now we're going to get our opposite there. Okay, so again, this right here is going to be 1. And so this one over here is going to be 1. To the 0th power, we're going to write down x to the 3rd. This one right here, since this is 1 less than n, it is just going to be n, so that's a 3. Hopefully you can see that. Again, this one right here is symmetrical to this one, so it's also going to give us that as a 3. And then anything to the 0th power is 1. And that's a 1 because that's a 1, it's symmetrical. Dx to the 3rd. Now, as you move along, and you keep doing this and you get to the higher exponents, let's say you get up to 8, you have to remember that in your degrees of smallness, that's anything that's dx squared or above, is so minute that we can ignore it. So from here, we can ignore that. Let me make that a different color. We can ignore anything from there on. So let's just quickly, we're going to do the first 3 terms of 8. Okay, we're going to do x plus dx to the 8th power. And we're just going to do the first 3 terms just because, why not? We need to. We need to. Not much has changed in what I'm writing down. You can see I haven't erased a whole lot from our initial. So this first one is 8. This is going to be a 0, so that's going to be 8. And we're just doing the first 3 terms, okay? There's a reason for that. I did it right that time. And it keeps going after that. Now, what I want you to recognize in your degrees of smallness, remember you're looking for dx squared when you're looking for degrees of smallness. Right here, we have a dx squared. We don't look at that, past that. We assume that this is approaching 0, so anything times 0 goes away, right? And we're left with these two first terms. Since these are the same, this ends up being 1. That ends up being 1. We're left with x to the 8. And then this one, since that's 1 less than our n, our exponent is going to give us, or our coefficient, sorry, is going to just be that 8 there. We've got x to the 7th, dx to the 1st. And everything out after that, because that's a dx squared, that has a degree of smallness close to 0. Okay? Hopefully, if you have any questions, comment, ask us. Make sure you like, subscribe. Love you guys.